everyone. We have quite an exciting seminar series this year. Somehow the organizer was able to get people invited from all over the world. So we'll have all these international people coming to speak. Today we're going to start with someone, David Rollinson, who's now from Pittsburgh. Okay. David was born and raised in Virginia and came to Carnegie Mellon. He got his undergraduate degree in mechanical engineering around 2006. And he loved Pittsburgh so much, he decided to stay on and work at Red Zone for a couple years. And then sometime in around 2009, Scott Thayer called me up. And Scott said, hey, I got Super Dave here. And I didn't know who Dave was. He wasn't in my class, and I'd forgotten. So Scott just explained to me how we have to get Super Dave here to Carnegie Mellon. And one thing led to another, and he started his master's degree and eventually got his PhD in 2014. I was lucky enough to somehow convince Dave and a couple of others from my lab to continue to stay in Pittsburgh and start a company called HEBI Robotics. And right now, HEBI is advancing some of the technology that we started developing in the lab. Last week, I was kind of not sure, how do I prepare to introduce Dave? And I asked him, and he reminded me of this Super Dave thing, okay? And I knew about Super Dave, and then Dave explained to me there was a second reason why we called him Super Dave, and that's because he got hurt a lot, okay?
That was the main reason, actually.
Okay, so in that point in time, since he told me that, to now, he's since gotten hit by a car, okay? Now, I don't know why people are laughing that he got hit by a car, it's kind of weird. But the thing is, he got hit by a car, and now he's explaining how it's harder to get better. He rides his bike every day. So I thought, in honor of the Super Dave name, we've gotten this little gift.
Oh, Jesus.
Okay. He got me this sweatshirt, by the way. So I figured it'd be fair to get him this Super Dave sweatshirt. So I don't know if you want to wear it now. It'll cover the microphone.
We can. Yeah, the Amos will do it. We can kind of display it. We can have it on display during the talk there.
I'm looking forward. I'm sure we're all looking forward to Dave Rollinson giving us a fine lecture. So
all right.
Dave.
Thank you. All right. Cool. So as Howie said, I'm here from HEBI Robotics, and I'm going to give a talk that is in basically two parts. It's going to be about the technical background behind a force-controlled actuator that we make, and then a little bit about about the company that's actually making that actuator. So this is both kind of from my personal perspective, kind of the mechanical side of talking about the actuator and the technology, because that's basically my contribution to the team, and then kind of my perspective as an engineer who's now more and more involved in the business side of running and hopefully growing a company. So the goal of HEBI Robotics is to make building robots eventually as easy as building with Lego. Right? We want anybody to be able to build a system, and we want to be able to do it in a way that they're not even thinking that it's a robot. Right? We want this to just kind of be creating the next generation of tools that people think about in the same way you think about hammers, screwdrivers, power tools today. It's just something else that amplifies and augments human creativity and work. Right? That's what we want to be accomplishing. That is a long ways off. That will keep us busy probably until the day we die, if not beyond. But what we have right now are a set of building blocks that we're creating that are used by researchers that is, I think, rapidly advancing people's ability to build robots and deploy them in the field. So one of our first customers was the Robotics Institute, the FRC, and they had a project where they needed to sample sorghum stalks. So this is a couple years old. And what they did is they needed to be able to just sample things that were always vertical. So they just needed a couple degrees of freedom. So they were able to use our modules, put them together, get an arm that was lighter, simpler, and cheaper than taking an industrial robot and trying to do the same thing or inventing something of their own from scratch. And actually, in their case, the arm was the first thing that was up and running because it was really just building blocks put together. So they had at least that part of the demo going very early, which traditionally they would have thought would have been the hardest. One of my favorite examples right now is NASA Ames, which has built a tensegrity robot. So if anybody's been behind the Carnegie, there's a sculpture that kind of raises up, but it's all built with cables going vertically. So picture that sculpture. I'm forgetting the artist's name, I'm sorry, but actuated, right? So the idea is this thing can pack into weird shapes, but be compliant. And this is also an example of customers doing kind of whatever they want to our modules. They send us these videos, and we're like, oh, holy cow, here comes the repair bill. And they say, no, everything still works. And I'm going to talk about kind of why that's important, and some of the technology we've chosen kind of enables that. And I always thought that controlling snake robots might have been the hardest thing to figure out how to make move. But trying to make this thing move in a reasonable way, I think actually might be more difficult, which might be why they hired a snake robot guy to do the controls for it. I don't know. And then lastly, some of our customers just buy single modules and make robots using a single degree of freedom. So this is a guy who basically makes bolt-on autonomy kits for cars. And he told us that's what he did. And we're like, oh, that's neat. So he'll probably be doing something in simulation or I don't know what. And he sends us this video saying, hey, it works. And us engineers looked at that and said, oh, wow, that's pretty freaking awesome. And Bob, our COO, says, I'm going to spend some lawyer hours and revise our liability policy. So it's really cool seeing kind of what people do, right? I'm really now kind of more and more inspired by the creativity of what people are able to do. So I'm going to dive into kind of the technical side now of that actuator, that little red thing that you saw in all those applications. So I'll start off by talking about kind of what is an actuator. It is kind of maybe a vague term. The dictionary doesn't really help because it says it's a mechanical device for doing something. But I think that's actually pretty close. And when I think about actuation, the problem I'm trying to solve, kind of start to finish, is I want to go from a motion that I want, and that motion could be positions or it could be velocities, or we think it's very important to also think of motions in terms of forces, and then actually do that, like finish that. Take the thing that I want in my head that I can write out on paper and actually execute it, and hopefully even help me figure out what that is. So kind of at its core part, you need, I'll say, a motor. I know there's different types of actuators, but for the purposes of everything I'm thinking about and talking about, we'll be talking about electric motors. But it very quickly kind of spirals out to other things you might want. Like a transmission, you're going to need a gear ratio because motors are high speed, low torque. You need high force, high torque, low speed, generally. Now, if you want to actually do something, you might need sensors. Once you have sensors, you'll need to close the loop with motor controllers, communications. You want to be able to mount it. There's all these other things that you need to add. It's just an actuator. It's much more than just a motor and gears. And lastly, a big thing that we work at HEBI is APIs and software tools to basically also help out with going from what you want theoretically to actually executing it and coordinating it. There's a big difference between going from one widget to now coordinating a bunch of widgets, whether it's an arm or a leg or even something weirder. So actuation is probably, people think of it as maybe a very mature field, maybe not the most interesting thing. It's not as cool as maybe self-driving cars or other things. So why are we choosing to work on actuators? The quote that I like that sums this up is from Jerry Pratt in an article from the New York Times back in 2015 when Uber came and, I'll say, disrupted the RI. Said, if you're well-versed in the area of robotics right now and you're not working on self-driving cars, you're either an idiot or you have more of a passion for something else. So Jerry Pratt is not an idiot, and he's extremely passionate about walking robots and humanoids, and he's one of the best in the world at it. I might be both, but I'm definitely passionate for actuation. And that is because I believe that actuators for robotics today, the kinds of things that people in this room are trying to do, I don't think actuation is really a solved problem. They're big and they're heavy for starters, right? We want to be able to move things out of kind of an industrial world and have people around these objects. And they need to be maybe on the body. They might need to be mobile. So power and weight is kind of a big part. Generally, actuators that you can go out and buy today usually have poor force control. That's starting to change a little bit, but I believe that moving the peg in terms of what robotics is going to be able to do really involves controlling force in addition to positions, and perhaps making some other trade-offs on the way of doing that. If you try to solve these two problems above, you're going to wind up with something that's either expensive or custom. And then lastly, generally it's also complicated to coordinate. Like even if you've made the system, trying to do the fancy things with it is difficult. So we're trying to incorporate other sensors like vision. We're trying to basically handle things that are much more complicated than the industrial blind, just do the same thing for 3 years sort of approach that robotics has done. So the first step toward, I think, trying to solve these problems is something we call the X-Series Actuator. And so it's everything that I kind of mentioned there before wrapped up in a modular package so that you just give it power and Ethernet, and then everything else regarding motion control is solved. So anything on a standard network can send commands to it, positions, velocities, or torques, either from graphical tools that help you kind of debug, get up and running, stuff like that, as well as APIs so that you can actually write code to do it like you would with a normal robot. In addition to the sensors that are for motion and sensing the motion, we have things like IMUs embedded so that you can quickly incorporate that into your loops or make balancing robots or understand the orientation of your arm on the fly. And since we're on a network, we can basically use other sensors that might be on the network. So all of your cell phones have IMUs, gyroscopes, accelerometers that you can sense the motion of. In this case, we're just taking the velocity from the phone, feeding it to the actuator, and our APIs also provide all the tools for handling dynamics, trajectories, all the things to basically be able to smoothly control this weight from a simple signal on the phone. And our customers can use as much of that or as little as they want. It's like some people are experts in dynamics more than we are, and they'll throw those layers out and do their own thing. Lastly, every part of our all the actuators we make are series elastic actuators, which means they're compliant. And that means that it's easier to control force, it's easier to sense force, and it's a little bit safer to be around in the sense that impacts aren't as hard. It's kind of like a shock absorber. So in this case, we're swinging a weight around, but we're still sensitive enough in our control that we can interrupt that, react to it. And then the final part of the video, the big reveal, is everything spins around and ta-da! The whole thing was filmed on a 6 degree of freedom arm built out of our own actuators with the idea that we want to be able to do fun stuff like this. I can't really take credit for the video if Nico's here. I don't know if Nico's still hanging around. Nico Zavalos did this video. This whole thing was his idea. And we still have that mirror, Nico. You can pick it up anytime you want. So kind of the highlights again, it's a series elastic actuator. I'll explain what that is a little bit. It's modular. We focus on it being really power and torque dense, really more torque dense. We focus on having very, very large gear ratios and going slow if that's what's necessary. And we believe in simultaneously controlling position, velocity, and torque. And one thing I should say is if anybody has questions, feel free to interrupt kind of as we go. Otherwise, I'll just barrel through it. But I'll have, OK, Chris.
What is HEBI?
HEBI? HEBI is Japanese for snake. Next question. No, it's so we came out of the snake lab, and really just to start off with, we thought we might be building and selling snake robots. And it turns out that by the time you've gotten a snake robot even a third of the way to doing something useful, you could have made a custom system that does the same thing, but it was still a pain in the butt. So what we decided to do was basically take the modules of a snake robot, make them more general purpose, and HEBI was also short, and the fact that nobody really knows what it means we could still change our minds later on and maybe not have to change the name of the company. But then it turns out that like our biggest single market is Japan, and everybody asks us why we're called HEBI Robotics. So cool. It's also a backronym for Heritage Biorobotics also. Yeah. Nah, that's all right. So why would we choose series elastic actuation? So if you want to control force, which that's kind of what we're going after, one way to do it is if you have electric motor. One of the really awesome things of electric motor is that you can have your torque constant, and you know your motor current, and you multiply those two together, and you get your force. Yay! But if you put a gearhead on it, like most robots have to do, this could basically, you might as well just put a not equal sign in some case. So like if you think of certain gearheads, if you're a mechanical engineer, maybe you know about worm drives, or basically things that aren't back drivable, right? You could put a gearhead on a motor that supports basically infinite load with no work from the motor. And so you could try to use that to sense your force kind of at your own peril, and in general it would not work. So some guys at MIT in the 90s, Gil Pratt and Matt Williamson, came up with the idea of a series elastic actuator, which is basically a fancy word for saying I'm going to put a spring on the end of my actuator, and I'm going to use that to basically make controlling force easier. I'm going to low pass my actuator, and I'm going to solve some things kind of an engineering way as well, in the sense that sensing force is actually pretty hard, but sensing position is really easy. So I can now sense the displacement of a spring, and if I know the spring constant, figure out my force. So I've turned that force control problem into a position control problem. And so when we focus on creating, all right, a new series elastic actuator, what are the parts that we want to focus on? We've got motors, gears, and springs. And all three of these are actually really mature technologies, right? Like motors have been around for 100 years, and there are some really great ones if you're in robotics. Kind of no matter what scale you're working at in robotics, you have a great selection of motors that you can purchase for what you want. Gears are also kind of a very mature technology. You have everything from harmonic drives on the high end to really well understood, well engineered commodity spur gears that you can even customize on that end. And where we kind of found we wanted to focus our efforts, as strange as it was really on that spring. which I'll get to in a minute. But the series elastic actuators basically have advantages, and this is whenever people talk about series elastic actuators, they usually list these three things in order: better force control, energy storage. So if you're making a walking robot, or especially a running or a hopping robot, a spring will let you get by with a much smaller motor, right, like a pogo stick, and also shock protection. It's like the suspension of your car, and is actually, this is the part that now I stress the most, honestly, that if you're going to make a modular unit and give it out to people that can do whatever they want, that shock protection that you get from series elasticity is, I think, one of the reasons why we are not eating it in support costs right now with all the crazy things people do. But there's no such thing as a free lunch, so it comes with drawbacks. When you make your system compliant, you're deliberately making the trade-off to make your position control worse. So the more compliant you are, easier it is to control force, but the harder it is to control position. And you're adding complexity. You're adding springs that weren't there before. You're adding sensors that weren't there before. Your control loops on how to handle this becomes more complex. So the electronics, the software on the module itself becomes much more complicated. And even at a high level, coordinating things is more difficult. When you have a big stiff robot, you can really kind of sweep, I think, a lot of things under the rug by commanding positions and cranking up the gains and calling it a day and telling people to get out of the way. But with a compliant robot, you have to think about dynamics. You have to think about gravity. You definitely have to think about smooth trajectories. And so you have to give people the tools to do this stuff, because while it's not necessarily like an unsolved research problem, it is error prone, it's tedious, and it can definitely slow down research if you're trying to do all that from scratch. So as I talked before, the thing we decided to really focus on that seems weird that we thought was lacking was really the spring. So kind of the core part that we embarked on, this was while we were still at CMU in Howie's lab, was designing a spring, as small and compact a spring for a series elastic actuator as we could go about. So the main person that was kind of, I think, leading this design, certainly in his experience, was Ben Brown. And he should know a few things because he's made like some of the world's best pogo sticks. So when he tells me how to design a spring, I'll definitely listen. And he said, well, the space constraints are really, really tight. So let's look at the energy densities of material. So if you're designing a spring, what matters is how much energy can you store either in a small space or for a very light weight. Because we care about being light, we care about being small. And both by volume and by mass, the energy density of rubber is just kind of through the roof, like 3-4 times higher really than any other material. And in practice, it winds up getting exaggerated by this even more, because if you're using steel and fiberglass, when you're designing something, you have to leave all this negative space in your design for the thing to deflect into. Whereas in rubber, you're just stretching it. And in our case, we're just shearing it. So as a material, it gives you a really good design space to work in and a really good efficient space of what little space we did have in the snake modules as we started designing this. When most people try to use rubber, they use it in tension and compression. That tends to wind up being nonlinear, which kind of out of the gate, we would prefer to have something linear so that we don't create a huge modeling problem for us kind of to start off with. So we found out that if you shear rubber, it's roughly 3 times less stiff, so that gives us more compliance. We can have that explore lower ranges of that spring constant, which for snakes we were really interested in doing. And it winds up being a lot more linear. And so what we wound up designing at the end of that effort was something that was a steel plate that was glued on either sides of pieces of rubber. But the design of the plate is important. The bonding of the rubber is important. Working with people that know how to do kind of all this materials, working with rubber is important. Fortunately, Ohio next door is still the rubber capital of the world, and we've worked with some great suppliers over there that know what they're doing. And then we did a trick where we tapered this cross-section to basically use the rubber even more efficiently, improve the strength. So if you have a conical profile, so this thing's shearing, right? Like take a donut top and bottom and twist it like that. If you have a conical profile, the rubber is at a constant shear angle anywhere in it. And that holds for any dimension as long as that cone intersects, right, at the middle. And so that's a design that we came up with at CMU, and CMU patented, and HEBI has the license for, and we're off to the races. And kind of some of the early papers on it kind of demonstrate the linearity. When people are looking at springs, you're kind of looking at the displacement torque or displacement force curve. So a straight line would be a linear spring. Yeah?
What's the longevity of the rubber? How long does it last?
It depends what you're doing to it. If you're so what we found out from the snakes kind of after the fact is if you start getting up into this range, you might be in the thousands to tens or hundreds of thousands of cycles. What's interesting about rubber is like we're still kind of learning about it a little bit, but there's definitely like a heat dissipation sort of thing where you could do a load where the rate matters a lot, right? You could go to a huge load, come back, huge load, come back. But if you do it like over a longer period, it will last pretty much indefinitely. But if you were to like double the rate, the thing might fail in a day. So it's a kind of the failure mode is interesting. And one of the things that we've done as HEBI is we have a much bigger factor of safety. So the snake springs were really kind of under designed and would go out into this bit, right? This is shearing to almost like 45 degrees angle, right? And the springs that we use now kind of stay in this regime. And one of the reasons for working with a rubber supplier, we asked, hey, we're using natural rubber, is that okay? He's like, oh yeah, these are actually what are in the bushings underneath a Ford F-150, and they last for like 5 years, so you'll be fine. We're like, sweet. But we definitely did some poking around, and there are some kind of non-intuitive failure modes that we've discovered. Yeah?
What's
40A? 40A is the durometer. So when you're specifying rubbers, that's another really great design parameter we like of the rubber, is once you have the shape, you can have it molded, and you can specify kind of anywhere from like 30 to 70 durometer. 30 is really soft. I'm trying to think of something like a 30 durometer rubber might be like. It's not, what? Skin, okay, yeah. And 70A, like an eraser, is like 60 or 70, something like that, I think. Yeah, 70's pretty hard, right? And so it's not like a linear scale. It's not like 50A rubber is like 3 times as stiff as 40A rubber, stuff like that. The scale's kind of weird. But it basically, just by selecting a different rubber from the mold, we can have just the same spring cover a wide range, in addition to kind of adjusting the geometry. And yeah, so we've looked at natural rubber and neoprene. Yes?
Sooner or later, you run out of travel, and the thing gets very stiff.
When you're compressing it, you do. In shear, you basically eventually just shred it, right? It's like a rubber band, right? It goes and goes and goes and goes, and
So maybe I should have said.
I guess it's not a rubber band, but
you want it to become
sometime you would want it to become stiff. You're asking if I believe in nonlinear stiffness?
Wouldn't you rather have a nonlinear stiffness? Because then you can, by changing how much the string stretch, change the stiffness, and all sorts of funky things. Plus, it protects the device.
I agree with you.
Can I get a share of whatever's
Do not comment on future products. Yeah. Yes. We chose linear stiffness to start off with. I think there are advantages of nonlinear stiffness. Alex Scheppelman worked for us for a little over a year. Some of his ideas definitely rubbed off a little bit. Nonlinear stiffness also has the advantage that you're softer around 0. So kind of no matter how strong your actuator is, you do generally care about force control around 0. So being softer there is good. Yeah, I think there are a lot of advantages to nonlinear stiffness. Any other questions? This is good. And one other thing I'll say is I think damping is a good thing for a lot of robots. Whenever you read a lot of papers about series elastic robots or controlling series elastic robots, there's usually like a line somewhere in the middle or the end that's like, man, we had to incorporate a lot more damping than we thought we did, and we're doing it all with the motor. So in our case, I think the fact that you lose a little bit of energy in the spring I think helps in controllability, right? And if you think about off-road vehicles, you have dampers, right? And they're like mad, and you dissipate energy left and right, all in the name of controllability. It's when you really, really care about efficiency is where you might want to get that out of the system. And right now, we're mainly using it, I think, for shock protection and force control, energy storage to some degree, but that's kind of lower down on the priority list in terms of what we're looking to get out of series elasticity. So on kind of a more industrial design standpoint, people ask, why does it look like a tape dispenser? And we tried a couple different things, and we wound up with this weird shape really because it was function over form. So whenever you're doing design, you kind of start with constraints. So we knew we wanted to use spur gears, so we weren't using a very exotic transmission. We knew the motor we wanted to use, so we basically designed around the spur gears we knew we had to have and the motor we were going to use. We wanted to use standard connectors, and so we built around just a standard RJ45 connector. And after doing that, I know why they're like disappearing from laptops is because the connector is enormous. So once you design for this connector, we knew that we wanted to have a through bore for wiring to keep the system really clean, be able to have high dexterity at our wrist, be able to spin around. So the bore has to fit that RJ45 connector, and it has to be 15 millimeters. We have to have a rubber spring, and we want to have a giant bearing on the output so that people don't have to do a whole lot of extra engineering to put it together, even if they're chaining together kind of long things from a base module. We want it to be like Lego, where like if it looks like things go together, they should just go together. And exploding away on the inside, I used to try to tell people not to take pictures of this, but now if you Google HEBI Robotics and click image, like the third link or something is a teardown of our actuator, so who cares? So the inside looks like this. Basically, the lid comes off and that bears all the support. The last gear in our gear train is actually really large, right? So we wanted to have, even though we have multiple gear ratios, we need to kind of design for the largest, the heaviest torque, the highest force, and you have a very large gear with relatively large teeth. But then the other thing that kind of goes in well with this design, which is why the spring design that we've designed really is good for spur gears, because that last stage has to be very large, and this was true even back in the snake robots. So you have all this negative space that you're going to make empty anyway just to save weight, but that's kind of exactly the space where the spring sits. So the last gear is actually on bearings in here, so this gear basically rotates around the hub, and the spring is that coupling between kind of the timing notches in the gear and timing notches that are on the bottom of the hub. And then we sense kind of both sides of that for our deflection. So it fits in pretty elegantly, at least from the spring design. And the other reason we chose spur gears was so that we could have multiple gear ratios in the same package. So if you have two shafts that are the same distance apart, and you could basically pick the right number of teeth so that you're either engaging your motion on closer to one shaft or closer to the other shaft. And so using to that, we can get basically a 6-to-1 dynamic range from our high speed to our high torque, which is pretty wide for something of the same size. So that means that our high torque end is almost 6.5 times more torquey than our high speed end. So for the same amount of power, we can cover a wide range, which is important for making things like arms, because the shoulder requires a lot more force than something like the wrist, and you don't want your wrist to be slow. And so if you look at things like harmonic drives or a lot of other gear reductions, you're kind of in this 50 to 150 to 1 ratio. So you kind of have a 3-to-1 range. And the fact that you're in the 50 to 151 means that a lot of choices have already been made for you in terms of the kinds of motors that you can use. Whereas we have a wide dynamic range, and we kind of have as whatever choice we want in terms of gear ratios. So we'll see that we kind of took some pretty extreme end choices on kind of what kind of motor we were going to pick. So other people we were kind of influenced by, talking to Aaron Johnson, working on Rex, talking to Sungbae Kim at MIT, they're like, electric motors can kind of do whatever you want as long as you don't melt the windings. Very, very carefully, and as long as it's a brushless motor. So we're picking brushless motors and overdrive them like crazy. You want to think of it in terms of a transmission. So in our case, we chose these in-runner brushless motors for a couple reasons, but mainly that we could put a very large gear ratio on them, and they have the best thermal properties. So you want to heat sink your motor really well. And in this case, these outrunner motors, even though they spin at really high speed and need big gear ratios, the windings sit on the outside. So getting that heat away from the motor, which is the thing that limits your performance. If I'm looking through the Maxon catalog, the thing I look at now is in the bottom left corner where it says thermal resistance, right? That plus its capacitance kind of tells you how hard you can abuse it, assuming that you can give it as much voltage as you want. Kind of a weird thing about motors is I kind of think of it as like you pay for torque, but speed is kind of free as long as you can give it enough voltage. So we take 9-volt motors and we drive them at up to 48 volts, but do it very, very carefully. And that's all predicated on heat sinking your motor really well. So one of the reasons the actuator is designed the way it is it's all in the name of getting heat away from this motor. At the scale we're at, we don't really need active cooling. Just wrapping it aluminum and using conduction does most of what we need. At a larger scale, we might want to do something maybe fancier, but really like the most of your gains are made just by either blowing the slightest breeze you can or just wrapping your motor in metal. You don't have to go to liquid cooling unless you're really, really going for like Iron Man type performance, which we're not. And then really you want to model your winding temperature really, really, really well. So in a perfect world, I'd want a sensor in my coils telling me exactly how hot they are. But in reality, if you're already doing a lot of stuff on the module, you can do things to basically give yourself a sensor. You just you create a model on board using data that Maxon gives you that's pretty accurate. So when we look at feedback from an actuator, you get this, which is a sensor, like this green line that doesn't move. So this is from the snake robot where I was basically loading it really, really hard with my hand. And this is the winding temperature going up based on a model that we verified is really accurate. It's probably within about 5-10%. And in that space of time, the temperature sensor, which is literally touching the case of the motor, does not move, right? But there's a 2-stage thermal model that we can report back. And you might as well think that you have a sensor on it because we know the current, we know the winding resistance, we know the voltage, we know how fast the motor's spinning. We can use all that to tell you quite confidently how the winding is. I'm going to skip through the next little bit and get to kind of more of the business side, if that's all right, unless people have questions on motion control, position, velocities, torques. No? Oh, yeah.
Actually, I think adding the springs essentially first order filter so that you cannot achieve very fast control performance.
That's right. Yeah, you cannot get as good bandwidth, for control bandwidth on your position because you're compliant, right? So you're not going to have the superhuman repeatability, right? Like even if we solved all the engineering problems even with perfect sensing, perfect motor control, no backlash in our gears, if we took an industrial robot with all of that engineering in it, high-end engineering, and then put a spring on it, we would not have the repeatability at the cycle times that you get with an industrial robot. Right? That is explicitly a trade-off we're making with this technology.
Right, but do you have any plans in the future, for example, use steel or other materials and have a larger stiffness spring so that you can improve your
Potentially, right? One of the things that we say, and maybe it's a bit of a punt, is we can always put like a solid steel slug where that spring is now. Like we can make a stiff actuator anytime we want. Right now, I don't think that satisfies the need for what we're seeing with the market yet, but we could. But yeah, that's explicitly the trade-off we're making. And then this is a very generic slide, but smooth trajectories are really important. This is something we've learned. So we give people the tools to not just do bang, bang, go to position or rely on a controller to give you that smooth motion. We give you the ability to kind of explicitly coordinate joints. And I firmly believe in minimum jerk trajectories for just about any sort of motion you want to do. Yeah?
When you started off, why aim for like a force control actuator? Were there other force control actuators at the time?
That's a great question to skip over this and get to the next part of the slide. All right, so I will get to your question in just a minute in terms of why we were doing a force-controlled actuator. And it'll be a little bit of a tongue-in-cheek answer, so if that's not satisfying, you can push me on it again when we get there. So why start a company? Howie has the best explanation as to why start a company, and particularly why start HEBI, why start this company, and that was to keep the band together. All right, so the top row are the founders of HEBI Robotics. It was Howie, so he's had the Snake Lab for, I don't want to say a long time, but a long time. And then these are all people that came into the Snake Lab and the stars aligned and we had all the bases covered for really doing robotics development. So Matt Tesh was doing software engineering at the same time as doing his PhD. I came in and was doing mechanical engineering based on my past experience while I was doing my research. And Florian did some amazing software development that basically was the foundation of what are now all of our APIs for control. And Curtis is our electrical engineer that was able to pack more and more things into the Snake module. We had all the bases covered for technical development. We worked really well together. We had kind of that Vulcan mind meld like a good band has, right, when they're working together. And we've continued to grow that team and kind of keep that spirit. And so the big part of it, I'm going to go back. I want to go back. The big part of it is, so why do this as a company? Why not just do this but do it at CMU? And the tongue-in-cheek answer is our funding was up, but we weren't done. And the other part of it is the things that we were focusing on were really kind of more and more away from research, right? We weren't really focusing on cranking out papers. We wanted to start creating the tools so that other people could crank out papers and do really meaningful research in the way that we thought we were. So in 2009, that's when I joined the lab. It's kind of as a basis of comparison. This is the robot we called the Unified Snake. This had just started and came online when I joined the lab. And it had kind of was the first time we had really reliable hardware, right? Before this, we were building a Snake robot every year, probably pretty much because we had to, I think. Like Aaron was actually in the lab in those days, and they were very high maintenance. And this was the first robot that was really reliable enough that people were starting to use it for PhD research. So we were building on that. And then about 2 years later, a guy named Gil Pratt, the guy that invented series elasticity, came along and started a DARPA program that also kind of became the DARPA Robotics Challenge. And he had a whole part of it focused on actuation. And he basically said, hey, I'm paraphrasing, Howie can correct me if this is wrong, if you guys make a series elastic Snake robot that could control forces, I could fund it. And we said, okay. I don't know if that's okay. That's a good summary. And so I had not even really heard of series elasticity at that time, right? I went and looked up about it and talked to Ben Brown about it because he had been involved with it kind of since the early days. And we decided that for a Snake robot, force control makes a ton of sense, right? The way snakes move through the world isn't through position control. Like if we've worked a little bit with Dan Goldman at Georgia Tech, and you put different pegs in the world, they adapt, they comply. Whatever they're doing to get around those pegs, it does not exist in deliberately specifying joints, right? They might be maybe they are very simple wiggles like we're doing, but maybe those wiggles exist in force space instead of position space. Questions like that. And we want to test this in the real world. So we said, yeah, actually, let's make a really compliant robot that can control forces. And so by 2014, we got this robot. And in addition to being series elastic in a very small package, it was a really well-timed kind of point in the world where a lot of other things were becoming miniaturized, and we could go from serial to full 100 megabit Ethernet on the module. We could run a real-time operating system on the module, sensing for our encoders, sensing for IMUs. A whole bunch of other things had gotten small enough that we could now throw this in the module. So there's a lot of kind of practical technical advancements in the world that advanced at that time. And brushless motor controllers. We were able to go to a brushless motor at this point in time because you can now buy chips that are the size of your pinky that control brushless motors. And we've been growing ever since. So when we were still kind of part at CMU, we were still supporting the lab, but all the hardware development, the Snake part, moved off campus to a beautiful building called the Design Center. I think the next photo should show it. Oh, you can't quite see it. I cropped it out. There's a gutter system in this room because the ceiling leaked a lot. And so, but it always leaked from the same cracks that you can see in the ceiling. So we set up gutters and then we piped it all down to the edge. Yeah, and then Howie was in for one meeting, and this was like early on when it was like really bad, and you couldn't really notice that it was leaking because the gutters were doing their job. And one of the building guys comes in and says, "Is the ceiling leaking?" And we're like, "Just in the usual places." He goes, "Okay," and he leaves out. And Howie's just like, "What?" And then we did stop complaining to the building guys because the first time we complained, they gave us a bucket. Right? Right? So then the second time, we said, dude, the ceiling's still leaking. They came in and said, there's our bucket. And they took it and they walked out. So we're not there anymore. We're in this building in Lawrenceville called the Chocolate Factory. And we have more space, but we're starting to fill that up too. It's a little bit more of a subtle transition, but that is yesterday. So we're kind of starting to burst the seams at this space. So we're not growing like Silicon Valley 2x every year style, but we are growing, and it's kind of neat, at least for me to look back, kind of see that perspective. So I'll close out the talk with kind of what are the things that I worry about. When I first kind of started with HEBI and was moving from finishing PhD into HEBI, the things that kept me up at night were all kind of technical questions, like, we want to take the spring and like have other people use it. How long will that spring last? Have we been doing the right tests? What should the overall form factor for it to be if it's not a snake robot? How do I get gears that have the right strength, that have the right lifetime? How do I find the right suppliers to make all of this at the quality I want? These were all like technical things, that I was focused on. That's what kept me up at night. Nowadays, what keeps me up at night is revenue, right? Which I guess is kind of a duh, but like we're choosing to try to make a company that we're self-funding as much as possible. We are selling. When people ask us, well, how do you make money? And we say, well, we make a widget and then we sell it for slightly more than it costs to make it. And people are like, whoa, right? But that comes with its own risks, right? There are good months and there are bad months, right? So it's not like a subscription thing where we kind of have this baseline. It's a good source of revenue that we have, but it's really bursty and it's really, really stressful. And so I'm trying to think about ways of how to make that more reliable. Focus. One of the things that I've heard people thrown out about startup companies that I totally believe is your biggest cost at a startup is opportunity cost, right? The most expensive thing you can do is focus like mad on something that's not worth it. Especially if you have like an amazing team like what we have at HEBI. So I'm paranoid that like every day we're working on the thing that we should be working on, if that makes sense. Communication. It was all really easy and really fun when it was just the 5 of us. And like I said, we had that Vulcan mind meld, and we all sat around the table. If we had a question, you just say, hey, Matt. Hey, Curtis. Hey, Florian. Hey, Howie. Right? But as the team grows, you actually have to be a lot more explicit about the communication. And I'm actually learning that you don't necessarily want to have everybody on one big channel. There actually are some pieces of information that are better to compartmentalize. Like, you don't necessarily want to be talking about the financial numbers every month because in the grand scheme of things, that's stressful. And it doesn't help to stress out the entire company about that. We should always stress out a few people about it. Culture. I am paranoid about culture, kind of especially over the things over the last year. So culture, people state their values, their core values, the things that they wouldn't change even if they become disadvantages. But really they're written down, they're important, but that's really kind of like the reflection that you can see of a culture. And so the culture of a company is something that I now believe is baked early on with like the founders and the people that they hire, and it's almost impossible to change. And it can be an amazing advantage until the moment that it isn't, right? So like if you look I don't want to get too controversial, but if you look at Facebook, move fast and break things is really, really great when you're a startup, but maybe not so great if you're the way that the plurality of the world connects to each other, right? Maybe there's a little bit more responsibility involved there. There are people in this room that are great people, have amazing attention, amazing understanding of the technology, that made decisions that are mind-bogglingly poor at Uber, right? And that's because of culture, right? These aren't bad people, but the culture is what influences people, even good people, what they do when nobody's looking. And so kind of at the foundation of all of that is hiring. Our single biggest challenge as we grow, the single biggest thing that I lose sleep over is hiring and how to grow the team without screwing up any of those things that you see above that. One of the best books that Bob, our COO, has recommended me that I really liked is one called Good to Great. And the foundation of that book that really resonated with me is first who, then what, right? Like before you can even do anything, you have to have the right people on the bus. You could be a baseball team and say, hey, we're going to win the World Series, but until you assemble, the Yankees or the Astros or whatever, you're not even going to have a chance because you're just wasting your time. So kind of with that last note, we are hiring. We're hiring full-time. We're hiring interns. Just kind of anybody. We're hiring assembly technicians. We're really just looking for great people all around, and we're hiring more for kind of potential, right, than anything else. So I'll finish with a thanks to everybody here, and a thanks especially to everybody else at HEBI. And if you want to learn more or geek out, there's the websites there below. And thank you guys for your time. Chris.
Why are you doing this in the United States?
By this, you mean like starting the company or doing the manufacturing? We are making widgets.
Chinese graduate students tell me that they can make $50,000 robots for $3,000 in China, and specifically Southern China.
Yep.
Why don't you just outsource to Southern China?
Because it's not actually that easy. And for some components, we are, right? So I would never have thought how complex supply chains are, but we are a company that involves, our supply chain involves as many countries as we have employees, okay? We have parts from China, we have parts from Taiwan, we have parts from Japan, we have parts from Switzerland, we have parts from Germany, we have parts from Austria, we have parts from Canada, we have parts from the United States. I'm probably forgetting somewhere. At one point, our magnets came from the Czech Republic, but now we get them also from Canada. So, right, it's complicated. There are parts that we do make there that are cost effective to make there. One of the things that we're at that we've learned is being, for us, maintaining manufacturing of that, doing all the final assembly, doing the testing, that is what drives our own engineering more than anything else. And if we were to outsource that, we immediately cut ourselves off on the legs in terms of development, in terms of our ability to make a product better, because at least for where we are, it's not a one and done sort of thing. Like every batch of 50 parts that we make are slightly different, better in ways that are either for manufacturing or better for the customer. And there's also IP stuff, right? Like the most critical thing that we have on the modules is the firmware, and we want to retain very tight control over that. And we don't want any interruptions to the development cycle on that. We don't want any interruptions to the security on that. So I think people who dive headfirst into China, like for certain things that may be absolutely the right move, but the story I think is a lot more complicated than people are.
But sometimes it's involuntary. So Boston Dynamics is now sort of centering on mini spot, and saying we're going to make a business out of that.
Yep.
And then you look at China, and they're cranking out mini spot ripoffs.
Yep.
For a lot less money.
Yep.
Have there been any mini heavy ripoffs yet? And when it happens, what are you going to do about it?
I'm not aware of any straight up ripoffs yet. We have a couple competitors, right, that are doing sort of the same thing, but there's not the blatant HEBI ripoff, right, that's trying to undercut us. And if they do, basically, our only hope to compete is to do basically what I said before, is maintain the ability to keep innovating as quickly as possible, right? You can't stop running. That's our only hope, right? Because you're not going to sue people. I'm not going to spend any money on lawyers that I'm going to use to hire people or do capital improvements for equipment. Our only choice is to run as fast as possible and not stop.
Do you want to comment on software?
If anybody has a question on software, I'll try to answer it.
In regard to Chris's point, in other words, do you think our software also
I mean, I think our software is, if we have a secret sauce, it's the software. That's why I'm not afraid of teardowns, being out on the internet. It's like, oh, it's a motor and there are gears and there's a circuit board and you can see the components. Like most of the hardware, almost every single thing in that actuator is customized in some sort of way. But it's the real secret sauce for us is the stuff we're doing in software to juggle standard Ethernet communications, control the motor that way, provide simultaneous control of position, velocity, torque, and the ability to upgrade it, right? So all of our modules that we've ever shipped over the last 2.5 years can actually be upgraded. So like we have an IMU in every module. We finally added a pose filter, so you can get like a quaternion pose out of that. That's an update that you can just get, right? And every actuator supports that. And for that reason, we encrypt it, right? So all of our firmware is encrypted. If the Chinese government wants to take a electron microscope and get it, I guess they can do that, right? But we've taken the steps to prevent. But it's also the easiest to copy, right? If you're somebody who would just get that straight up. So we have taken steps to try to prevent extremely easy stealing of the thing that we think is most important. Yeah?
What do you have to get rid of in your module if you want to reduce the price?
Performance. It's a great question, right? So Dynamixels, like a Dynamixel that competes with us, if you look at kind of their Pro or even the regular one, like we'll say the Dynamixel 108, 106, whatever it is, that's like $500 actuator, right? And if you open it up, you could see the compromises they're trying to make but can't, right? So the gears are really small and they're undersized. They have a factor of safety of like 0.5, right? Like they wear out, they break. The motor is all wrapped in plastic because that's cheap, right? And so the performance suffers there. But they're still using a Maxon motor, right? Like I'd be really interested in what percentage of the bill of materials of a Dynamixel is a Maxon motor. And so to hit that price point, right now, I don't know how to do it without making the exact same compromises that are already in a Dynamixel that have their limitations. The biggest single one that might change is Ethernet. Right? There's things that are limited in terms of being able to do research. Like one of the things that allows you to go really fast is we have more bandwidth than you could possibly need for motion control. Right? So that's how we can have IMUs that you send back with everything else, like full feedback, full floats, and like real units. You're logging it all. In people that are doing like RoboCup, I found out the humanoids there basically have like a test mode that runs at a very slow rate, and then in performance mode they turn off all the feedback, right? So that you can get something close to like 50 or 60 hertz on the control for the system. And for us, that's not a limit, right? So in the future, we might be able to make something that has the same hardware compromises, but bring Ethernet into it. That might be an approach. But as of right now, I wouldn't know how to really do that without making the same compromises that everybody else is already making. Yeah.
In the foreseeable future, what do you think? Which type of customer base would be the biggest, either research lab or industry or commercial sector?
Hope industrial. Probably. I mean, so where the company started off, right, is we came out and we said, all bright-eyed and bushy-tailed, we are going to take these modules and force control, and we are going to completely revolutionize the world of like small assembly, things for like small manual tasks, right? We're just going to go do that. That's hard, like really hard, like way harder. And even we thought we were realistic, and we were so far short on that. So fortunately, we found out that there are thousands of other people around the world that have the same research challenges we did, and we have something that's actually useful for them today. So let's hit that market. I think going forward, we will creep into industrial applications, looking more toward things that just aren't in a factory, right? So things that you might want to automate that are outdoors. So one thing we're looking at is kind of industrial inspection right now. So maybe moving things like an ultrasound probe, right, in a way that doesn't need to be industrial precise, but needs to be way better than a person can do. Or even if a person's doing it, just verifying it, right? And something, or things where, stuff like that. I think there are applications that will get there gradually, and that will be just a component of. But I think hopefully our largest market is something in like manufacturing and industry. But the honest answer is I don't know.
Another technical question.
Yeah.
All this based on assumption you want to use conventional motor and traditional transmission. What about exotic motor, exotic transmission?
I am yes, yeah. So Lily's referring. For a year and a half, I tried to build a cycloid drive, and that didn't work. That's the simple answer to that. And that's a good beer conversation if you want me to talk about that. But I do think transmissions are the Achilles heels of robotics. I'm way more interested in exotic transmissions than I am in exotic motors. I think the power density of motors is there. I think the price for power dense motors is there. The ability to control them cheaply is there. But going from high speed to high force is the limitation, both in cost, expense, weight. If somebody is sitting on a low cost, infinitely variable transmission, let me know, because that's what I want in my dreams. Yeah. Yeah.
Would it be great if we can tune the stiffness of this
I don't think that's as nearly as important as I used to think it was. For a lot of for some tasks, yes. So, in my mind, the use case for that really might be I have some task. If I'm going to do something where I'm like maybe training it and then getting it up to like Data from Star Trek, right? Have you ever seen him move? Like those sorts of speeds where he's like and do that, then yeah, I'll need to change the stiffness to do that. But I think for a lot of practical applications, you can kind of pick one stiffness if the assumption is that you're making up with it for other sensing, right? If I'm using other touch sensors, force sensors, especially vision, depth sensors, stuff like that. So yeah, I guess I could see a scenario in which stiffness would become the limiting factor, but I don't see that being the limiting factor for variable stiffness. And I'm also going off of other people that were really into variable stiffness that weren't anymore. So like Jonathan Hurst now doesn't think you need variable stiffness, and he was a huge proponent of that. And his working on making legged robots, he says you don't need it. I'm getting everything. He's got the same thing as me. He's also has a company. He's starting it up. I've got a lot of headaches, but tuning the stiffness of my actuators ain't one of them.
So if there's no more questions, I'll ask two just for fun. So the first one is, what surprises did you have? As you said, we set out to do some industrial assembly, and that didn't happen. But maybe at a technical level or any kind of surprise.
Okay.
What's the surprise?
That's a good question. I would say the biggest surprise was that we found a market with almost no advertising. Now, to be fair, that was the third thing we tried to sell. We tried to sell a snake robot, and turns out nobody wants one. And then we tried selling tweaked versions of the modules of the snake robot, and nobody wanted those either. And then we made a third one and told just a few people, and the fact that it's growing by word of mouth, right, without us doing any, we don't actually have a full-time salesperson right now. We basically go to ICR, we go to IROS, and we put out cool YouTube videos every now and then, and that's what's driven all of our sales. That's been probably the biggest single surprise, a good one at that. And my other, if I were to pick a bad surprise, is how hard it is to find the right people. It is super, super difficult. I was not prepared for how hard that is.
Okay, so I'll ask one more question. So a lot of people here all want to start companies now. That's, trend is swinging up. And you said, well, we're not growing really fast like the Silicon Valley companies are, and you may have referred to Jonathan Hurst's company growing fast, and you're proud that we're growing slowly. So
yeah.
You want to explain that?
Yeah. I say we're not growing, but we're 10, 12 people. So I guess in 4 years we've between double and tripled. So I guess that's growth. That's a lot.
You know what I mean?
Yeah, I do know what you mean. I don't think the world of venture capital is well matched for robotics, especially robots that make hardware, or people that make hardware. That is a paradigm that definitely works for certain companies, and I don't. Yeah, I guess the short answer is I don't think it's well matched for a lot of companies in general, but especially robotics companies that are making hardware, because I don't think it's realistic to expect 100x return in a few years for something like this. It goes slower, and that's why when we've looked at investment, we look for industrial partners, strategic partners, and if we look for future investment, it'll be more of the same thing. People that kind of understand kind of how long that road takes, and I think that trying to apply kind of the VC grow fast and fail template actually winds up stifling maybe a lot of innovation in the long run, and that there's a lot of things that get started and then abandoned and forgotten and then started again and abandoned and forgotten. So I'm not against growth by any chance. I'm not against investment. But I want to have realistic expectations and take investment from people that understand. Because I think robotics is really overhyped, and we already kind of had one round that we did where we kind of overhyped ourselves. Like, we honestly all thought we were being realistic, and the thing we were tackling was way harder than we thought. And we weren't even trying to overpromise, right? We're stretching it a little bit. Like, we all thought we were being really honest with ourselves.
So where did your money come from?
Are we allowed to say?
Can we just say a strategic partner?
I'll just say a strategic partner.
That's a good answer. Yeah, go ahead.
I could tell you when the camera's off, I guess.
Yeah, maybe you should say strategic partner.
Yeah.
And it can come from customers like you.
Oh, shameless.
That's all I got. All right, well, thanks. Let's thank you. I'm sure Dave will stay around for other questions. Otherwise, I'll usually.